Okay, guys, this will be a teaser to the 30-minute video I'm working on right down here. In that video, it's going to talk about what I call the smoking gun, the cracks. We're always looking for a smoking gun. On the FIU bridge, the smoking gun are a few details, and part of those details are mentioned in, okay, I can't remove that one yet. And the report, or reports, memos, question marks that go back and forth about the deflection after span one after removal of the false works. This was a question on March 8th. It was also a question on February 28th. This will be part of the video down here, and I'll go into it back and forth of what of the smoking gun of the cracks, but I'll also show how Linda Fig and the concept of their design is kind of confusing to them. Not to blow it off, but this is this is Denny Pate, Linda Fig's engineers responding. And if you look at the small print, it'll be much better in the video. He states that on March 8th, it's 2 days before the move, they do not have, through extrapolation, we know they do not have the answer back as of this date, 2 days before the move, of why these other cracks are presented. He states the deflection is just, it's expected deflection. Let's talk about that expected deflection. The deflection, I can theorize, is in the middle. Even though we have the break here and here, I think this is more like a crack or a brittle break fracture, like a cracker breaking here and here at the time of the failure, the load being, the deflection happened, the stress is resolving here and here. Watch how I'm in that video. I'm going to just hide this into the video also. So this is kind of a double video inside this video. So this would be a steel pipe. They're secured with bolts, steel bolts, secured. Nothing to elongate. No. They're a pinned connection. It doesn't slide or move. These are permanently locked in connections. Now watch when this is the member or the canopy. If this bridge has deflection, watch what happens when I deflect just a little bit in the middle here. Do you see what happens with the deflection? At this joint here, it starts pulling down on it. But it has no choice to pull down on it. Pulling down on it would create if this just pulling down only, it would start pulling this. Want to pull this over. This on this side connected here would want to resist that. So you're going to get some failure at some point. You're going to start getting failure. Some failure, it will start happening. The bolts aren't going to be able to hold that structure from deflecting. But we have 1, 2, 3. You got to combine them all. How much an effect they would have. But she states there for resonance, not for supports. Although she calls it a cable stay bridge and a couple of other times cable stays. She goes back and forth. But deflection causes, see the deflection down, will cause the stress on this connection here, and including the middle connections, the connections all the way both directions. The least amount of deflection would be just using the scale here. You can see the least amount of deflection would be down, closer. This moves a 1/2 inch. Well, did I get that right? You move a 1/2 inch here, least deflections on the outside. So you see that the stresses are still there. You just can't get it though. See how I move that down? That's deflecting down. That puts this in compression. Yeah. It's trying to get smaller. Let's do this. Just do this. I said, yeah. Okay. So that's our one that's going in tension on the bottom side, and on top is compression. I want you to look at it I want you to look at it as concrete. So the top side of the concrete is the very top of this. Oh, I can make it bigger. Okay. Let's do that. So the very top of this, if I can point down, the very top of this purple is in compression, and the very bottom side of it is in tension. It's wanting to pull apart. That's the tension side of it, wanting to break. So when you get that deflection, you're getting some compression and the tension moments on the top member and the bottom member individually. The top, doing this again, puts this in compression. Let's do a little bit more exaggeration. So it puts this part in compression, and the outer side, you can see it's clearly had a stretch. It becomes in tension. that all helps the structure fail. If this is in place, if this pulls down, now watch what happens. I had it up top. Now what happens when I pull this down? It also wants to pull these joints apart if these could stay in place. But remember, they do have some secure anchoring here at the 12. This level number 1 rather sits on the deck. So if you try to pull that down, the resistive force wouldn't be equally bending together. They all have to interact, so they're creating, part of that slide friction that would be going on there if it could move. Otherwise, it just fails. If it can't move, it just fails. If it hits an abutment, something that's non-movable, it just fails in buckling, if you will. I'm going to be happy saying buckling. If it could move out of the way, then we could say it sheared it off. It sheared it out of the plane. And that's the down here. But we have a bar in there which would resist that shearing off, pushing it out of the plane. Oh, this video is getting too long. I'm going to terminate it. This is my teaser video for the down here, but we can come back to that. But I show it to you in my scale model anyway, but this is this model version. All right, guys, let's step it up.